Hello, today we will start with chapter 3, which is motion in 2 dimensions. I will just remind you of this slide where we looked at various motion of some objects. For example, if we look at the water here and we look at it properly, we see that it's not moving only in 1 dimension. It's actually at some point changing the direction of motion. It's the same thing with this dolphin. It's not moving left, right, up, down, down a slope. No, it's changing both. It's changing direction at some point. The same thing with this ball. If we look in particular at the ball, for example, the player here, he throws the ball from the initial position 0, 0, and it reaches the bucket, which is 1 meter above from the initial position. Okay, so the y of the ball changes by 1 meter, and the x changes. If we look at the from the foot of the guy until the wall, we find that it changed by 4.1 meter. Okay, so the initial position was 0, 0. The final position was 4.11. So both x and y changed, not only x changed or y changed. And this is why this is 2-dimensional motion, because both x and y change. Okay, so if we look, this is how the displacement is changing. And this type of motion that looks like this, we call it projectile motion. Okay, you just have to remember this, that this is called projectile motion. Just like if we drop an apple and it goes down, we call it a free fall. Okay, or if we drop some keys up and then they go down, we call it a free fall. This type of motion that has this this image, we call it projectile motion. So how does the displacement change? Both x and y change. Now the velocity, so just remember the Angry Bird story, that it all depends on how I initiate my velocity where this ball can reach. Okay, so this is now a footballer and he is hitting the ball with a certain V initial. Okay, now V initial is a vector. Now V initial is a vector. It's not only in 1 dimension, it has 2 dimensions. So you remember this vector, if we have vector f, it has fx and it has fy. And if I want to calculate fx and fy of any vector, it's just whatever this vector is. In this case, it is v0. v0x is v0 cosine theta. v0y is v0 sine theta. Okay, so this is what we were studying about vectors. So this is how v0 is changed. This is what v0 now. Okay. And what happens to the acceleration? So we now know that the projectile, the displacement changes, the velocity now has 2 components, even the displacement has 2 components, and this is why we say it's 2 dimensions. Now it has, the first component is the x component and the y component, okay? And also the velocity, initial velocity also has 2 components, but what happens to the velocity after the ball reaches the leg of the guy? Let's look at the acceleration. Now, just like in free fall, the acceleration during the projectile, it's also constant, and it's equal, the ax is 0 and the ay is -10. Okay, so this you need to memorize. Ax is 0 and ay is -10. What does it mean that ax is 0? You just remember from 1 dimension, if ax is 0, implies the velocity is constant. Okay, if a is 0, the velocity is constant. But here you just have to pay attention that it's no more called just a, it is ax. Okay, so now vector a has 2 components, ax and ay, where ax is 0 and ay is -10. Ax is 0 implies Vx is constant, so whatever, and this will be equal to V initial x. If I have V initial x, which is from the previous slide, V initial cosine angle theta. So if I have V initial and I have angle theta, then I know what is Vx through the whole motion. However, Vy is changing because Ay is -10, it's constant, so Vy is actually changing. Let's have a look. How do they change? This is how the V vector is changing along motion, okay? It's a V vector, it's in dark blue. It's in dark blue. V0, it's V0x and V0y. Then along the whole trajectory, so we call this trajectory. That is يعني الخط اللي هو عم يمشي عليه الطابق. We call it the trajectory. So at this point, for example, notice that Vx is equal to Vx here, to Vx here, to Vx here, to Vx here. Vx doesn't change, okay? Vx doesn't change because what? Ax is 0. Because Ax is 0, so Vx doesn't change. What changes? The Vy changes. Now look at this. This is very tall. This is shorter, shorter, shorter until it reaches 0. And then it flips. It starts going down and faster and faster and faster and faster. So this, if you can just remember during a free fall, what happens to the velocity when the ball is going up? When it's going up, the speed is going, you hit it with the velocity, then it goes down, 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 down until it reaches the maximum, then it flips, then it goes down faster, 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 faster until it reaches the ground, okay? So the same thing is happening here with the Vy, only with the Vy. It starts with V initial sine theta, that's the maximum value of it. Then it starts decreasing. Look at the vector. I draw it like this so as it gives you an idea that it's decreasing, decreasing. Over here, actually, there is no Vy. At the highest position, at the maximum height, Vy is 0. And Vx is all of V. So Vx is all of V. Then it flips. Then it flips. It becomes negative, 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 and faster, 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 faster. Okay, let's look at some equations. In one dimension, we had delta x because it was only moving along delta x, or in one dimension. It only had V, it only had A, and this V was plus or minus, and this A was plus or minus, depending if it's moving left, right, up, down. In projectile or in 2 dimensions, now we talk about delta X, delta Y. So we don't only have delta X, now we also have delta Y. And the velocity vector also, now it has 2 components, Vx, Vy. And the acceleration, it also has 2 components, 0, -10, and you just memorize this. Okay, let's look now at our equations. In one dimension, these were, I will focus on these 3 equations. I'm not writing here delta x equal half the initial plus the final into delta t because no need, we will not use it during projectile. So in one dimension, this is the first equation, this is the second equation, and this is the third equation, okay? In projectile, each equation becomes 2. Each equation becomes 2. Each equation becomes 2. So delta x, it will become delta x and delta y. V, it will be Vx and Vy. Vf, it will be Vfx and Vfy. Okay? Now, instead of V0, it will be V0x. Instead of A, it will be AX. Now, if we're talking about, so let me focus one by one. Let's say we are talking about delta x, okay? So delta x, it will be V0x plus half AX delta t, okay? If we're talking about delta y, instead of V0, it will be V0y. Instead of A, it will be AY. And the same we do for all other equations, okay? So we do the same for all other equations. So let's start. This is Vx, this is Vx. So this is now Vx, it will be V initial x plus A, this is A normally, it will be AX. If we're dealing with VY, it will be V initial Y plus AY. And the same applies to the last equation. But we have to keep in mind that AX is 0 and AY is minus 10. So now I go back here. These are exactly these equations. So I go now to my projectile equations. Every AX I delete it, no need, it's 0. All AX are zeros. And all AYs are minus 10. So AY minus 10, AY minus 10, AY minus 10. In the following slide, what is the final version of the equation? So this will be just V0x delta t because AX is 0, so it's canceled. Here there was minus 10 over 2, so it's minus 5. Vx will be equal V initial x, Vy will be V initial y minus 10 delta t, and Vf squared equal V initial y squared minus 10 delta y. Here is just the result of these equations after plugging 0 for AX and minus 10 for AY. So I get these 1, 2, 3, 4, 5 equations, okay? And instead of 3 equations in 1 dimension, we have 5 equations in 2 dimensions. Let's start actually by an easy exercise to see how we apply these equations. So this is page number 16, number 3. So in the sport of dock jumping, dogs run at full speed off the end of a dock that sits a few feet above a pool of water. The winning dog is the one that lands farthest from the end of the dock. The dog runs at 8.5 meters per second. So what is this piece of information? It runs at 8.5 meters per second straight off, straight off. Straight off means this, what you see in green, okay? It doesn't go up, 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 and then down, down, down. No, it just goes straight, straight. So how much in this case is V initial x? How much is it? Whenever you start with the projectile motion, the first thing you do is you calculate V initial x and V initial y. So this is a vector which is along the x-axis. How much is the x component of it? It is V, all of V initial. If you just study the previous 2 lectures, you will know why is this the case. Because here the angle this red vector do with the green, it's 0. So cosine 0 is 1. So Vix is Vi, which is equal to 8.5 meters per second. V initial y is 0 because the vector is along the x-axis. Okay, so this is the first piece of information we have. What else do they give us? They say that the dock is 0.61 meters above the water. So I know that this distance here, it's 0.61 meters. Okay, so let's go back here and put some more information. If I have this, what does it mean? What do I have? Do I know what's the distance from up to down? Yes. So what do I know? Delta x or delta y? From up to down. From up to down implies this is delta y. It's equal minus 0.61 meter because it's in the opposite direction to the y-axis. The y-axis is upward. This is going downward. Okay. What else I know? I know that AX is 0, AY is minus 10. Anyway, it's already put in my equations. Okay. So part A, determine the time taken by the dog to reach the water. So the first question is, let's write it here, find delta T. So I have V initial X, I have V initial Y, I have delta Y, and I want to calculate delta T. So which of these 5 equations I should use? We do exactly as we were doing before. I come to the first equation. Do I have delta x? Do I have delta x? Delta x is from here to here. It's how much it goes on the x-axis. Do I have this distance? No, I don't have this distance. So I don't have this distance, then I cannot use the first equation. Let's try the second equation. Do I know delta y? Yes, I know delta y. Do I have the initial y? Yes, I have the initial y. Delta t, it's asking me about delta t, so I need it. And also here there is delta t. So I can use this equation. Okay, so delta y equal v initial y delta t minus 5 delta t squared. V initial y is 0. So I have delta y minus 0.61 equal 0 minus 5 delta t squared. Delta t equal 0.61 divided by 5 under radical, it will give me 0.122 seconds. Okay, this is part A. Part B, how far will the dog go before splashing down? How far, it means delta x. Okay, it's written here. So how far, it means find delta x. Now I go to the equation of delta x. Delta x equal v initial x, and I know how much is v initial x, times delta t, and I know how much is delta t. So I use it and I calculate delta x. Let's do another similar question. This is page 17, number 2. A ball, a ball is thrown horizontally. So again, like the previous question, the initial is horizontally. Horizontally implies it has v initial x equal v initial and v initial y equals 0. Okay, you keep this in mind. It's thrown horizontally from a height of 20 meters. So I have this distance here. It's 20 meters. Okay, with a speed of 5 meters per second. So he's giving me this information that v initial is 5 meters per second. So directly I say v initial x is v initial, it's 5 meters per second. V initial y is 0. And I know that he's giving me delta y from up to down, it's minus 20 meters. Okay, first part, find the time taken to reach the ground. It's exactly like the previous question. So I know that I have to use the second equation because it has delta y, it has v initial y 0, and I want to calculate delta t. So I use, this is equation 2 actually. We use equation 2. Sorry, it's difficult to go. You use equation 2. Delta y is equal the initial y delta t minus 5 delta t squared. Delta y is minus 20 because we take the y-axis upward. Okay, always take the y-axis upward. This is y-axis and this is x-axis. So minus 20 is equal v initial y, which is 0, minus 5 delta t squared. You do the calculation, delta t is 2. Here it should be plus or minus 2, but time can never be negative. Time can never be negative, okay? Now part B, how far? Again, how far? So he's asking about delta x, which is this from here to here. So we use the first equation because I have the initial x and now I have delta t. So it's 5 times 2, which is 10. Part C, this is new now. Part C, determine the velocity at impact. Determine the velocity at impact. Between parentheses, he's saying he wants the magnitude and the direction. So what happens at impact is that this will be the velocity vector. Let's put it in another color, or let's erase this. So at impact, this is what's happening. This is the velocity vector at impact. It's asking for its magnitude and its direction. So first, I have to calculate how much is this V final. This is actually V final or V at impact. Okay, you can call it whatever you want. You can put this is point B and this is V at B. You can call it the way you want. So how much it is? In order to determine the magnitude of a vector and the direction, we have to remember that the magnitude is square root of the x squared plus the y squared, and the angle is the tan inverse of the y component divided by the x component. So we have to get the x component of the VF and the y component of VF. We just come here, these two equations, they have the x component and the y component. So the f component of the x component of this V final is V initial x, which is equal to 5. Remember that the x component doesn't change. So all the way, it will be the same value. So VFX is equal V initial y. So I use this equation. Okay. Now, for VFY square, I have to use this equation. It's equal to V initial y minus, I use the last equation. Actually, I can also use this equation because VFY will be minus 10 times delta T that I've calculated. So I would get the same answer. Yeah. Vy will be minus V initial y minus 10 times 10, which is 100. Yeah, whether we use this equation or this equation, we will get the same answer. So over here, I used this equation, but you can use this equation and you would get the same answer, which is 20. Okay. So I will get here VFY square equal 400, VFY equal plus or minus square root of 5 of 400, and it must be minus because if you look at it, it is downward. Okay, it is downward. It started moving downward. So VF is 5 minus 20. We want the magnitude. The magnitude of VF is the square root of the first component squared plus the second component squared. So we get V final as a magnitude is 20.61, and theta is equal tan inverse to the y component divided by the x component, and this will be 20 over 5, actually minus 20 over 5, and theta will be minus 76 degrees. Okay. So this is the end of today's lecture. Tomorrow's lecture will be revision for the exam on Friday, and the live session will also be slight revision. If you have questions, I will answer them, and if you don't have questions, I will be working on chapter 2 during the live session. So this is it for today. Bye-bye.